Validation of IaaS-based technologies for 5G-ready applications deployment. The involvement of vertical industries in the design of 5G mobile networks is crucial to guarantee the adoption of the new ecosystem, and for this reason, their needs should be considered as high-priority drivers of the design. For example, including cloud-like environments would provide vertical industries with a familiar environment and lower the barrier for creating 5G-ready applications. The cloud architecture allows a clear and effective splitting of roles among the main actors involved. However, it still needs to be proved if the current infrastructure as a service-based cloud operating systems are suited for fulfilling 5G stringent key performance indicators. The same goes for network orchestrators. So, in order to assess the suitability of current IaaS technology for fulfilling 5G application requirements, this paper has exploited the CNIT S2N testbed to perform a validation of a complete 5G ecosystem. The testbed is a multi-layered, multi-tenant hardware and software facility for the advanced experimentation and demonstration of 5G edge and cloud computing technologies. It supports a telecom network platform developed within the Matilda project and can host multiple isolated tenant spaces that can emulate complete full 5G network environments. This slide shows the main components of the testbed. It can host multiple isolated tenant spaces as project environments that can manage and configure the respective physical virtual resources through a Metal as a Service approach and the software elements through Canonical's Juju platform. The testbed has hardware capabilities for setting up full 5G network environments, complete with user equipment radio and wired access, programmable connectivity, security system, and geo-distributed computing domains. The autonomic management of the lifecycle of 5G network slices and edge computing resources is realized by the network platform layer of the Matilda framework. The main functional blocks composing the telecom layer platform include the operations support system that manages all functions and operations for the placement of a vertical app over a slice and maintains the information on all the consumed and available resources. Then there is the NFV orchestrator, realized using open source Mano, for the lifecycle management of the network services, both those composing the base 4 5G services and the ones provided to slices. The wide area infrastructure manager is based on the Ericsson Network Manager and manages and monitors the wide area communication resources. The virtual infrastructure manager, based on OpenStack, abstracts and exposes computing, storage, and networking capabilities of data centers within the 5G infrastructures. Vertical industries can autonomically manage the lifecycle of their application graphs by means of vertical application orchestrators that interact with the OSS via a specific metamodel called slice intent that represents all the requirements that should be satisfied during the creation of a slice. The OSS has a highly modular architecture. All services are state-of-the-art cloud-native software, inherently parallelizable and ready to be integrated with the service mesh paradigm. The prototype is composed of 4 main software services and 2 databases acting as persistency layer. The slicing northbound module supports the communication between the vertical application orchestrators and the OSS. The OSS core module includes the virtual infrastructure manager and the wide area infrastructure manager convergence layers. The resource selector optimizer provides the optimization and reinforcement algorithms to be executed in the OSS. Finally, the NFV convergence layer provides a level of abstraction for managing the lifecycle orchestration of network services, virtual network functions, and physical network functions instantiated in the 5G infrastructure. Northbound, the NFV convergence layer communicates with the OSS core to interact with the resource selector optimizer during the negotiation phases that precede the materialization of a slice, and with the slicing northbound module for the following allocation of the network resources and the VIMs. Southbound, it interacts with the NFV orchestrator to drive the lifecycle management of network services and network functions, both physical and virtual. At CNFV, network service descriptors are composed of a predetermined number of VNFs, so network service graphs cannot be modified unless you destroy or recreate them. In Matilda, we have defined a generalized descriptor called network service blueprint. Blueprints have a template structure describing the logical architecture of the service graph in terms of types of VNFs, their interconnections, and the virtual networks to be used towards the outside. Single VNFs or groups of VNFs can also be annotated to be replicated in multiple service instances. Software plugins called VNF configurators provide all information regarding the D2 operation primitives for each VNF. The NFV service mapper acts as interface towards the OSS core, identifies the most suitable network services fulfilling the QoS requirements, and selects the corresponding blueprints. Starting from the information in the blueprint, the interface towards the NFVO, called NFV Service Setup, generates the package for the network service descriptor and onboards it on the NFVO. The S2N testbed has been used in this paper to assess the suitability of the existing IaaS-based technologies for supporting 5G-ready vertical applications. In the deployment, a wide area network interconnects 3 VIMs and 2 eNodeBs. VIMs 1 and 3 are considered edge VIMs, in the sense that they are placed geographically closer to the eNodeBs, while VIM 2 is placed in the core of the telecom infrastructure. The NFVO instantiates a public land mobile network as base network service. It is composed of a monolithic EPC in the core VIM2 and of additional bypass services in each edge VIM. The EPC has one network interface towards the access network and one towards the public internet. The bypass functions have an interface towards the wide area network to interconnect with the EPC and the eNodeBs, and one towards the virtual layer 2 network internal to the VIM. The dedicated OpenStack projects for the vertical apps are directly controlled by the vertical application orchestrator via connection to the public internet. Components of the same app placed across several VIMs require an additional network service to maintain the connectivity of the application graph. Several measurements have been performed on the Matilda testbed to compute the time required after the reception of a slice intent to deploy the corresponding vertical app. Times are measured for both the OSS and OpenStack. We have considered 4 application graphs, composed of a number of virtual machines between 4 and 7, and deployed over the 3 VIMs shown in the previous slide without any constraints on the proximity requirements. When a slice intent request is received by the OSS, the resource selector optimizer composes an aggregated graph based on the proximity requirements of the app component, and sends it to the wide area infrastructure manager, that computes a list of candidate VIMs fulfilling the requirements and forwards it again to the resource selector optimizer to select one of the solutions. This decision drives the initialization of an OpenStack project in each involved VIM to create the tenant spaces shown in the previous slide. These results show the distribution of the execution times ascribable to the OSS and to OpenStack to complete the operations I've just outlined. The bar on the left is a stack of the resource selector optimizer and wide area infrastructure manager execution times. The yellow right one is referred to OpenStack. These execution times are plotted over the application graph and the number of VIMs available during the test, and are reported in milliseconds for the OSS and in seconds for OpenStack. The OSS execution times grow with the size of the application graph because of the contribution of the 2 resource selector optimizer phases. Instead, the execution time ascribable to the wide area infrastructure manager is constant with the application graph size and only presents negligible variations with the number of VIMs. On the other hand, since OpenStack performs the same operations regardless of the application size, and each VIM creates its project independently, the execution times are not correlated neither with the application graph size nor with the number of available VIMs. These tests highlight how the execution times ascribable to OpenStack represent over 99% of the total, bringing the total deployment time in a range that is suitable for the IaaS context, but is definitely not acceptable for the 5G vertical environment, in which service agility is seen as a non-negotiable. Lifecycle operations on the NFV services are not parallel to the ones I just presented, but they are rather nested, as the day 0 operations triggered at the NFVO level start at the completion of the vertical app day 1. So, in day 0 of the network services, as I briefly said before, the NFV service mapper identifies the required network services and selects the most suitable blueprint for filling the QoS requirements. Then, with the information in the blueprint, the NFV service setup generates the descriptor packages and onboard them on the NFVO. In day 1, the NFV service setup asks the NFVO to instantiate the services and waits for all VNF managers to be up and running. In day 2, the service setup module retrieves the proper VNF configurators and sends the list of day 2 primitives to the VNF managers. Once all operations have been performed, the life cycle is completed. These results represent the execution times measured for day 0, 1, 2 operations on a number of network service instances spanning from 1 to 5. The graph shows the time ascribable to each individual operation that takes place upon reception of a slice intent to put into operation the network slice. Here we haven't reported data at varying number of VIMs, because it doesn't impact the execution time, just like in the previous results. Since the instantiation of the network services in the VIMs is sequential, times increase with the number of instances. However, the instantiation of the network service, which is the operation involving open source Mano, accounts for almost all the execution time, keeping the whole life cycle in the order of magnitude of minutes. This paper has investigated the suitability of the current cloud operating systems and network orchestrators to support the stringent requirements of upcoming 5G applications. We have exploited the CNET S2N testbed to perform a validation over a complete 5G ecosystem, including the most common reference projects and software suites. The evaluation has been carried out by analyzing the execution times for deploying applications and network slices. We have identified which contribution of these times are ascribable to the Matilda platform and to OpenStack and open source Mano. Results show how the algorithms operating the Matilda operation support systems scale with the number of instances and have negligible execution times, while both OpenStack and open source Mano are responsible for around 99% of the deployment of vertical apps and network services, bumping their lifecycle up to the order of magnitude of minutes. Thank you very much for your attention. If you have any questions, please do not hesitate to send me an email.